Hello students, so we're continuing with the Boolean algebra chapter, and from the previous video we've discussed this Kmap, and today also we'll be discussing about Kmap. So we'll be continuing with the pairing reduction method. So in the previous video we saw the following pairing reduction methods, that is pairs. So just a recap of what I've taught. So in pair reduction method we can group two variables of adjacent cells that has value 1. The variable which changes to its complement is eliminated. So the complemented variable gets eliminated in pairing reduction methods. Okay, so then to get the Boolean function, we to get the function f, we OR the two pair minterms. So the two minterms uh, is paired, and then we get the simplified sum of product expression. So pairing is done between two minterms. Now in terms of quads, in quads reduction method we can group four variables. So here two variables, and in here four variables. So four variables of adjacent cells that has value 1. So here in pairs it will eliminate one variable, but in quads it will eliminate two variables. So out of four variables, two variables will be eliminated. So that reduces the SOP expressions. So that also reduces the complexity of designing the logic circuits. Okay, the logic gate circuits. So the designing of the circuits becomes minimized. So it uses the less logic circuits. So now map rolling. So map rolling also, this is a part of quads. So it isolates isolated ones were paired to form a quad pairing. Okay, so all the isolated ones which have the map rolling is explained in the previous video. So all the isolated ones, it can be paired together, because isolated ones it complicates the designing of the circuits. Clear? So it has to be paired. Minimum it has to be paired. So if there are four isolated ones and it is paired, so it forms a quad. So in quads it becomes four variables. So that is achieved by map rolling. Now octet, in octet reduction method we can group 8 variables of adjacent cells that has value 1. So yeah, octet, okay, this is octet. Okay, octet eliminates three variables, right? So all this pairing reduction method we have seen. So in today's pairing reduction method, the continuation of it, we will see uh, the first one is overlapping groups. Okay, so overlapping groups. So just like map rolling, overlapping groups is also a different method. So here it is possible to use the same value, that means the value 1 which is assigned to the literals. So for more than one group, so it is possible to use the same value for more than one group. So the reason is isolated ones means more logic gates are required, as I've explained right already, to design the circuit, and increases the complexity. So overlapping between pair, quads and octet can be done. So that way it simplifies the circuit. So here is an example. Here first quad is formed by four minterms. So if you see this Kmap, so here we have four variables x, y, z and w, and these are the values that are assigned to the variables. So it is arranged in this order. So that means these four variables, this combination of values, that means each cells, right, each cells is a combination of these values. So that much combination of values can be formed, or mean term can be formed. So this represents one mean term, this represents one mean term value. These are the mean terms, right? So here you can see that here the first block diagram is a quad, and the second one is a pair, right? So in a quad you have four variables, this and this, and in a pair you have two variables, so this and this. and it cannot be this 3 because to form a quad you need 4, and to form a pair you need 2, and to form an octet you need 8. So these three numbers, these three ones, it cannot be paired together because there is no such thing as 3. It has to be either 2, 4, 8, right, or 6, like that. So this is a pair. So as you can see here in this diagram, this particular one value, or this 0 1 1 1, this particular area is shared by this quad and this pair also, so that is called as overlapping. Okay, so that is overlapping. So if it is not overlap, okay, so we'll come to the example here. First quad is formed by 4 mean terms, that is this mean term, this mean term, and this mean term, and this mean term, right? So we remove two literals, y and w. So how do we remove this y and w? So since both changes its form, so that means y changes to y complement and w changes to w complement, and so on. So if we see the position of the mean term, if we find out the mean term, so f equals to the expression x complement y complement z w. So that is represented by this one 1. So so here you can see that 0 represents x, 0 represents y, 1 represents z, and 1 represents w, right? So this is 0 means the complement of x, so x complement y complement z. Since it is 1 1, so z and w will remain the same. Okay, after that the next mean term is this, so x complement y complement, and then z is 1, and then w complement, so we get this. So it is OR, right? So as per the reduction method, right, we OR the mean terms, so all the mean terms are ORed. So next we come here, so that is x complement y, and then if we see the top side, z w, so that is this one, and next finally here x complement y, and then z w complement, so we get this. So now what we have to do is that we find out the variables which are complemented. So in a quad, two variables will be complemented, that is y y y complement y and y. So you can see that this variable changes, so it is eliminated. Similarly, w also changes from w to w complement, right? So that is also eliminated. So here the simplified SOP form we get as f equals to x complement z. Okay, now next pair is formed by two mean terms, so we remove one literal x as it gets complemented, so that is this one, this pairing, so which is x complement y, and then z w, and then again here x y z w, so which is this one. So here in pairs one variable gets removed, which is x, because x complement, right? So it changes from 1 to 0 or 0 to 1, like that, so that's why it gets removed. So now we have y z w, right? So now so as I have explained here, if we don't overlap this, if we don't overlap this, then what will happen is that, okay, this one will be separated, which is x y z w will be isolated value 1, which becomes complicated for while designing the logic circuit. Okay, so we so as much as possible the isolated ones we have to pair it with a different group, right? So now hence what we do is that we OR these two mean terms, okay, the first and the second. That means this mean term expression and this mean term expression we OR it, and then we get x complement z plus y z w. All right, so this is the simplified SOB expression, right? So you can see that all of this, okay, all of these mean terms SOP, it gets reduced to this. All right, so that's why designing the logic circuits becomes much more easier, okay, and it uses less circuits. So now redundant group, next one is redundant group. So a group whose ones are all overlapped by other group is called a redundant group. So that means when a pair or or maybe yeah, like that, it gets overlapped by other groups, is used by other groups. Okay, then so what happens is, so before writing the Boolean function, we eliminate any group whose ones are completely overlapped by other groups. Okay, so here is an example. The first pair is formed by two minterms, so we remove one literal. So you can see here, this is one pair, this is one another pair, and this is another pair. So this particular pair is sharing, is being shared by this and this, right? So this pair is completely overlapped by this and this, so we have to eliminate this. So this is not necessary, right? So what we do is that in the first pair, that is this one, okay, this one, here we have x complement, y complement, z and w, which is here 0 is stands for x complement, yeah, this one 0 stands for x complement, y stands for 0 stands for y complement, and then z and w. All right, again this side, x complement, y, z and w, right? So now all in here, y changes from y complement to y, so that's why we get this equation. Okay, and second pair is formed by two minterms, that is this one. All right, so here we have this equation, but the second pair is completely overlapped by the first and third groups, so second group is removed, so this pair gets removed. Again, third pair is formed by two minterms, that is this one, so we find the minterm value of this, that is this and this. Okay, and finally what we do is that the reduced SOP form is we OR this one, this and this, so that is x complement z w plus y z complement w. So we reduce all of these expressions, minterms, into just these two single SOP format. Clear? So that is redundant groups, right? Or removing the overlap pairs. Okay. Now, so based on that, we have one example here. Reduce Kmap for the truth table. Okay, you can refer to the textbook for the truth table. In the textbook it will be written draw the Kmap. Okay, so you can either draw the Kmap or you can reduce the Kmap, right? So if it says draw the Kmap, okay, then yeah, it will be in the reduced format also, so you can refer to the truth table from the textbook. Okay, so based on the truth table, what we have to do is that we have to draw the Kmap based on the truth table, and then find the position of those minterms whose value is 1. Okay, then we find the Boolean function of reduced SOP expression. So here, this you can see in this Kmap you have three groups. This is the first group, this is the second group, which is completely overlapped by this octet, and this is the quad, so which is separate. So now what we do is that first translate the truth table into Kmap. So the truth table is which is given in your textbook. Okay, based on that truth table, wherever the values are wherever the function values are 1, okay, so based on x, y, z and w, okay, x, y, z and w, if x is 0 and y is 0 and z is 0 and w is 0, then f will be 0. Okay, and if you see the truth table, it will be like this: x is 0, y is 0, z is 0 and w is 1. Then in f column it will be 1. Okay, and then x is 0, y is 0, z is 1, w is 1, f will be 1. Okay, so we are only marking in those minterm positions where the function value is 1, so we get this format. Now after translating that into the Kmap, reduction will be done, and reduction will be done first by the octet, then quad, and then finally pair. Okay, it will never start with pair, quad, octet. Always it will start with octet, then quad, and then pair. Okay, so in the octet format, okay, if you see here, this represents the first row. Okay, 1 2 3, and this represents this minterm represents the second row, right? So what we do is that in octet we eliminate 3 variables. So here you can see that except for x complement, here x complement x complement x complement x complement x complement x complement. All the other literals changes its form from complement to so it becomes complemented. So that's why y, z, and w gets eliminated. So the simplified SOP expression is f equals to x complement. So next, in the quad format, starting from here, this and this, we get this mean terms. We get these mean term values which are odd. Okay, so here also x and y remains the same because you can see that it's horizontal, right? So this is x and y, which all throughout it remains 1 and 0, that is x y complement. But for z and w, you can see that for every cell it changes 0 0 1 1. So it changes, it remains the same here 0 0, but here it changes to 1 1, and here it remains 0 but changes 1 1 0. So it becomes complement uncomplemented like that, right? So that's why z and w gets eliminated. So we get this x y complement. Now in the case of pair, since pair is completely overlapped by octet, hence it gets eliminated. Okay, so now the reduced SOP form is f equals to x complement plus or xy complement, right? So you can see that all of these mean terms expressions, all of this, it gets reduced to only this much. Clear? So this way, okay, it is very helpful while designing the logic gates. All right, so in the next video we'll be discussing about these logic gates here. That is also part of the Boolean expression simplification, right?